Alright, hi guys. We're going to be going through lesson 1.1, which is on sets. We already know that a set is a collection of numbers or objects, and we use these sort of curly braces or brackets, I call them the curly braces, to denote a set. And each element of the set is separated by a comma. So here's a couple of examples of sets. This is a set of numbers. These happen to be the 5 first prime numbers. Here's another example of a set. Again, you see the curly braces and the commas in between each element, and this is just to illustrate that you don't actually have to have numbers in a set. You could instead have letters or words or even pictures. But of course, in this class, we're normally going to have numbers inside a set. Now, there are several important number sets that you need to be familiar with during the course. The first one is the set of natural numbers. You notice that this n has got a doubled stroke in it. In fact, I sometimes denote it with a double stroke at the beginning of the n rather than the middle part of the n. But as long as it's got a double stroke somewhere, then we know that you're referring to that special set of natural numbers instead of some other set just called a regular old capital N. And the set of natural numbers are all the counting numbers, things that you knew about even before you ever went to school for the first time. They're the whole numbers, including 0, 0, 1, 2, 3, 4, and they go on forever. The next number set is the set of integers, and generally we double the diagonal line for that. And the set of integers is the same as the set of natural numbers, but now we're also going to include the negative numbers as well. The set of rational numbers, these are numbers that, a better way of thinking about this maybe, are the numbers that can be expressed as fractions. And for something to be a valid fraction, both the numerator at the top and the denominator must be integers. And so really we're talking about any number that can be expressed in the form a over b, where a is an integer, we'll get to this notation in a minute, and b is also an integer, but your denominator b cannot equal 0. You're not allowed to ever divide by 0, so it would not be a rational number if we had a 0 on the bottom. But we can have a 0 on the top, that's no problem. Now it's worth pointing out that, of course, our rational numbers can be positive fractions, they could be negative fractions, and even an integer can be expressed as a fraction. For example, 5 could be written as 5 over 1, and that would mean that it is a rational number because we can express it as a fraction. And the set of, the rational numbers, I normally double that part of the q. But it's really up to you, as long as you double some part of it. And then the set of real numbers, where we'll double the first stroke of the r, and that's absolutely everything that exists, every possible number, even the irrational numbers, as well as the rational numbers. Now I should just mention that with my rational numbers, another example of a rational number could be something like 0.4, this decimal, because we could rewrite this as a fraction 4 over 10, which incidentally simplifies to 2 over 5. Another rational number would be 0.33333, repeating forever. Anytime that you've got a repeating decimal, that can also be expressed as a fraction. But if you ever have a number that is not a repeating decimal, like 3.141596, etc., I can't see any repeating element to my decimal. This number, by the way, we know is pi, but that illustrates that pi is not a rational number. It is irrational. So to summarize, decimal numbers that end, or decimal numbers with a repeating part, like 0.333 or maybe 0.949494, anything that repeats going on forever, these are examples of rational numbers. But a decimal that goes on forever without anything repeating is not rational. This cannot be expressed as a fraction. Nevertheless, all of these rational numbers and all of these irrational numbers together do form the real numbers, because the real numbers include absolutely everything. Now, a number set with a superscript, for example, an exponent is like a superscript. It's an example of a little number that you write sort of higher. A superscript of plus, this includes only the positive members of the number set. So, for example, this n with a little plus beside it represents the set of positive natural numbers. 0 is not a positive number, so this one would just start at 1, 2, 3, 4 and go on forever. Meanwhile, a number set with a superscript of an asterisk includes only the non-zero members of the number set. In other words, we're removing 0 from the number set. So, z asterisk, which means the set of non-zero integers, would be all of the integers, but we're going to remove 0 from the set. So after writing our negatives, we'll now write our positives. And that is z star. Now we can use a Venn diagram to represent sets of numbers or objects. You guys might remember Venn diagrams are often drawn with rectangles and intersecting circles. Okay, but not all Venn diagrams look like this. So don't assume every Venn diagram looks like this. In this example, we're going to draw a Venn diagram that shows the relationships between the number sets n, z, q, and r. We know that r includes everything, so let's make a nice big circle for our real numbers. That includes absolutely everything. Inside our real numbers, we've got our irrationals and our rationals. So let's make this circle the rational numbers. And everything inside the real number circle, but outside the rational number circle, so all of the numbers here, those are going to be the irrationals. Those are the numbers that cannot be expressed as fractions. They can only be expressed as decimals that do not terminate, so they go on forever, and they do not repeat. An example of a number in this category would be pi. Now, inside the rational numbers, we have our integers. I'll denote those with the z. An example of a number, then, that is a rational number does fit inside q, but is not an integer, might be some fraction without 1 as a denominator, like 2 over 3. And then inside the integers, we've got our natural numbers, which we'll denote with an n. And an example of a number that is inside the integers, but is not inside the natural numbers, would be, say, any negative number, like, say, -1. So these are examples of numbers that reside in the outer rings of our real number set. And inside here, an example of a number that is a natural number might be something like 2. Now, from this Venn diagram, we can see that the natural numbers are entirely contained inside the integers. They are a subset of the integers, which are a subset of the rational numbers, which are a subset of the real numbers. The symbol, that's kind of like an elongated C with a line beneath it, that's the notation for is a subset of. So that is to say that if we said P is a subset of Q, that means that every element that is in set P is entirely contained. All of P is entirely contained inside Q. So every element in P must be an element of set Q. This means then that we can notate the relationship between the number sets n, z, q, and r in the following way. Remember that n is a subset of z, so n is a subset of z, which is a subset of q, which is a subset of r. And that's a nice expression that describes the relationship between my 4 number sets as illustrated in the Venn diagram. Now this symbol, which looks like a kind of a C, but this time the line's sticking out halfway instead of at the bottom. It looks kind of like an E. This symbol is the notation for is an element of. Or if we can put it into slightly simpler English, belongs to. And it's a way of describing whether something is inside the set or is not inside that set. Similarly, the symbol with that same E that's being crossed out is the notation for is not an element of. Or a little bit more informally, we can say does not belong to. Alright, let's look at a few examples of this. Suppose I gave you set M, which is the first 5 prime numbers, 2, 3, 5, 7, 11, and set N. You'll notice that this is an N without anything doubled. So this is just a set of numbers that I've defined as 3, 6, 9, 10. Because it doesn't have a double part, this does not mean the natural numbers. And that's why it's always important when you are referring to the natural number set to double one part of the letter. Here nothing's doubled, so it's not the natural numbers, it's this particular set I've defined as 3, 6, 9, and 10. Are the following statements true or false? So, if we read this, 5 is an element of set M. Is it true that 5 belongs to set M? Yes, it is. True. Is 11 an element of set N? No, 11 is not there. False. 2 is not an element of set M. Well, but 2 is an element of set M, so this must be a false statement. And lastly, 8 is not an element of set N. Yeah, that's true. 8 is not an element of set N, so that's true. Great. Alright, sets like M and N that we just looked at up here in this example, they have a finite number of elements. That is to say that we can count those elements. Finite is the opposite of infinite. And clearly we don't have an infinite number of elements here or here. We can count them, and thus these are known as finite sets. And we can use the notation n of set M to represent the number of elements in set M. It is also possible to have an empty set. That is to say, a set with absolutely no elements in it. And this kind of set, otherwise known as a null set, so empty set or null set, has got 2 different notations. We can show this with a set of curly braces with no elements in between them, or we can use this notation, a circle with a line through it. That is not a 0. A 0 is a number. This means there are no numbers at all, not even 0. It's completely empty. Sets like N, Z, Q, and R have got infinitely many members in them, and thus they are known as infinite sets. So, let's do an example. Suppose that we have this set N that we referred to previously, containing 3, 6, 9, and 10. Then N of N would be equal to, well, this notation represents the number of elements in set N. 1, 2, 3, 4. There are 4 elements in set N. How about the number of elements in the empty set? Well, there's nothing in the empty set, so the number of elements is 0. How about the number of elements in set Z, the set of integers? Well, we already said that's an infinite set. It's got an infinite number of members, all of the positive numbers and all of the negative numbers.